Time is one of the most fundamental aspects of our reality, yet it is also one of the most perplexing. It governs everything from the daily rhythms of our lives to the motion of the planets, stars, and galaxies. Time is something we all experience: the ticking of a clock, the changing of the seasons, the passage of days, months, and years. And yet, despite its ubiquity, we rarely stop to consider what time actually is. To embark on the journey of understanding time travel, we must first attempt to understand the nature of time itself. At a surface level, time seems straightforward. It is the progression from one moment to the next, a continuous flow from past to present to future. We measure time using clocks, calendars, and other tools, marking the passing of seconds, minutes, hours, and years. We experience time as a sequence of events. One event follows another, and we move through this sequence in an irreversible manner. But the more we investigate time, the more complicated and mysterious it becomes. Is time truly just a linear progression, or is there something more to it? The classical understanding of time. Historically, time was viewed as an absolute, unchanging backdrop against which events took place. In this classical view, time was seen as something external to the events occurring within it. This notion of time was formalized by Isaac Newton, one of the greatest minds in physics. In his 1687 work Philosophiae Naturalis Principia Mathematica, Newton introduced the concept of absolute time, a time that flows uniformly, regardless of the events occurring within it. In Newton's universe, time was a universal constant force, and it applied equally to all observers, no matter their motion or position. Time was the same for everyone, everywhere. In this framework, time was simply the ruler by which the universe's events were measured. It was considered separate from space and from the objects within space. Newton's view of absolute time served as the foundation for classical mechanics and remained largely unchallenged until the 20th century. Time and space, the birth of relativity. In the early 1900s, the work of Albert Einstein revolutionized our understanding of time. Einstein's theories of special and general relativity fundamentally altered the way we think about time, space, and their relationship to each other. In his special theory of relativity, 1905, Einstein proposed that time and space are not separate entities, but are part of a unified four-dimensional fabric called space-time. He showed that time is not absolute. It can be stretched or compressed depending on an observer's motion. This discovery was radically different from Newton's view of absolute time and laid the groundwork for understanding the relationship between space and time in a new way. The theory of special relativity reveals that time is relative. It depends on the observer's velocity. For example, if two people are moving relative to each other, they will experience time differently. The person moving faster will experience time at a slower rate than the person moving more slowly. This phenomenon is known as time dilation. A famous thought experiment demonstrates this principle. Imagine two identical clocks, one placed on a moving spaceship and the other left on Earth. According to special relativity, the clock on the spaceship will tick more slowly compared to the one on Earth, as seen by an observer on Earth. The faster the spaceship moves, the greater the time dilation. This revelation that time could be different for different observers was startling. It meant that time was not the constant universal entity that Newton had envisioned. Instead, time is relative and can be influenced by factors such as speed and gravity. The space-time continuum and general relativity building on his earlier work, Einstein expanded his ideas in the theory of general relativity, 1915. In this theory, Einstein showed that time and space are not just affected by motion, but by gravity as well. According to general relativity, the presence of mass and energy warps the fabric of space-time, causing time to pass more slowly near massive objects. This phenomenon, known as gravitational time dilation, can be observed near black holes, where the curvature of space-time is so extreme that time itself appears to slow down dramatically as you approach the event horizon, the point of no return. General relativity also predicted the existence of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. confirming another one of Einstein's groundbreaking predictions. The theory of relativity, therefore, gives us a much more dynamic and interconnected view of time and space, where time is not a fixed and unyielding entity, but one that can stretch, bend, and even disappear under extreme conditions. Time in the quantum world. While general relativity provides a powerful framework for understanding time on the largest scales, from the motion of galaxies to the behavior of black holes, it doesn't apply to the smallest scales of particles and atoms. Here, the laws of quantum mechanics take over. Quantum mechanics describes the behavior of particles at the atomic and subatomic levels, and it presents an entirely different view of time. Unlike the smooth, continuous flow of time described by general relativity, quantum mechanics shows us that time is probabilistic. It behaves in unpredictable ways. One of the most significant aspects of quantum mechanics is the uncertainty principle, introduced by Werner Heisenberg in the 1920s. This principle states that it is impossible to simultaneously measure both the position and momentum of a particle with perfect precision. The more accurately we know one of these properties, the less precisely we can know the other. This uncertainty suggests that at the quantum level, the concept of time and the certainty with which we experience it becomes far more fluid and uncertain. Time in the quantum world is also deeply connected to the idea of superposition. This concept refers to the ability of quantum particles to exist in multiple states simultaneously. A famous thought experiment, Schrödinger's cat, illustrates this principle. A cat inside a box can be simultaneously alive and dead until the box is opened and the state of the cat is observed. In this sense, time, as we experience it, can be seen as more fluid at the quantum level. Events are not set in motion until they are observed or measured. This brings us back to the idea that time, in the quantum sense, may not be a fixed linear progression, but a probabilistic series of potentialities. One of the most fascinating consequences of quantum mechanics is the potential connection between quantum entanglement and time. When two particles are entangled, their properties become linked regardless of the distance between them. This means that a change in the state of one particle will instantaneously affect the state of the other, even if they are light years apart. This phenomenon seems to suggest that time in the quantum world does not always operate in a straightforward linear fashion. Instead, particles can be connected in ways that defy classical understanding, leading some to speculate that time itself may be more interconnected and less linear than we realize. The arrow of time. One of the most perplexing aspects of time is the arrow of time, the fact that time always seems to flow in one direction, from the past to the future. This concept is tied to the second law of thermodynamics, which states that the entropy or disorder of a closed system will always increase over time. This increase in entropy gives time its arrow. It moves in the direction of greater disorder from low entropy in the past to high entropy in the future. This one-way flow of time is something we all experience daily, but it is not entirely understood. Time's directionality, however, is something that requires deeper examination. While the laws of physics are largely time-symmetric, meaning they don't inherently favor a particular direction of time, the increase in entropy in our universe gives time its observable direction. As we look forward in time, the universe moves from a state of order to chaos, and this transition is irreversible. This arrow of time is central to the way we experience the world, and it becomes even more critical when we consider the possibility of time travel. Time travel, a journey through time. Now that we've explored the nature of time, we can begin to entertain the possibility of time travel. The idea of traveling backward or forward in time has fascinated people for centuries. From the science fiction of H.G. Wells' The Time Machine to modern scientific theories, time travel has captured our imagination. But is it truly possible, or is it just a product of our imagination? The potential for time travel is deeply tied to our understanding of space-time. Einstein's theories of relativity show us that space and time are not separate, but are intertwined in a four-dimensional continuum. This opens the door to the idea that if we can manipulate space, we may also be able to manipulate time. If space-time can bend and stretch, as general relativity tells us, could we bend it in such a way that we could travel through time? In the next chapter, we will explore the theoretical possibilities for time travel, including the concept of wormholes, time loops, and the implications of relativity for time travel. While the idea of traveling through time remains speculative, the scientific principles of relativity and quantum mechanics provide the foundation for the possibility of time travel. But before we jump into those theories, it's important to understand that time, as we currently perceive it, is far more complex than it seems. The more we learn about the nature of time, the more we realize how little we truly understand about this elusive and fundamental aspect of our universe. Having explored what time is and how we perceive it, we now turn our attention to the tantalizing possibility of time travel. For centuries, the idea of traveling through time has captivated the human imagination, appearing in myths, literature, and science fiction. Whether it's H.G. Wells's The Time Machine or the modern iterations seen in blockbuster films like Back to the Future and Interstellar, time travel has become an enduring and popular concept. But while time travel remains firmly in the realm of fiction for now, the laws of physics provide a fascinating framework for understanding whether such an extraordinary phenomenon could one day become a reality. The question of whether time travel is possible, and if so, how it might work, is a deep one, tied to the very nature of time, space, and the universe itself. Over the course of this chapter, we will explore the theoretical foundations of time travel, diving into the ideas and equations that suggest that time travel may not be as far-fetched as it seems. Specifically, we'll examine Albert Einstein's theory of relativity, wormholes, closed time-like curves, and other concepts in modern physics that suggest time travel might, in some form, be possible. Einstein's relativity and time travel. The foundation of our understanding of time travel lies in Einstein's theory of relativity. Einstein's groundbreaking work on space-time reshaped our understanding of the universe and laid the groundwork for the possibility of time travel. As we discussed in Chapter 1, the theory of relativity tells us that time is not absolute. It can be affected by motion and gravity. This idea fundamentally challenges our everyday experience of time as a constant, unchanging force. One of the key principles of Einstein's special theory of relativity, 1905, is time dilation, the phenomenon in which time slows down for an object in motion relative to an observer at rest. This effect becomes more pronounced as the object approaches the speed of light. For example, an astronaut traveling at nearly the speed of light would experience time much more slowly than someone on Earth. This is known as time dilation due to velocity. At speeds close to the speed of light, time for the astronaut could slow to such an extent that while only a few years may pass for them, decades or even centuries could elapse for someone back on Earth. In theory, if an object could travel at the speed of light, which, according to relativity, is impossible for any object with mass, time would come to a complete stop for the object. While we have not yet been able to achieve these speeds with our current technology, this principle shows that time travel into the future is theoretically possible by traveling at relativistic speeds. This idea of time dilation has been experimentally confirmed with atomic clocks placed on fast-moving jets or in orbit around the Earth. The clocks on these high-speed objects measure time slightly differently than those on the ground, in accordance with Einstein's theory. Although the time difference is minuscule, the experiments show that time does, in fact, behave differently at high velocities. But what about traveling backward in time? Can the theory of relativity help us understand if it is possible to go back in time, and, if so, how? General relativity and time travel. Einstein's general theory of relativity, 1915, extends the ideas of special relativity to include gravity, and provides a more comprehensive understanding of space-time. According to general relativity, gravity is not just a force that pulls objects together, but is the result of the warping or bending of space-time caused by the presence of mass and energy. Massive objects, like stars and planets, cause space-time to curve, and this curvature, affects the passage of time. The closer an object is to a massive object, the more space-time is curved, and the slower time passes relative to an object farther away from the source of gravity. This concept of gravitational time dilation has profound implications for time travel. For example, near a black hole, where gravity is incredibly strong, time slows down dramatically. The closer an object gets to the event horizon, the point beyond which nothing can escape the black hole's gravitational pull, the slower time flows for that object relative to someone farther away. If an object were to fall into a black hole, it would experience time at an incredibly slow rate, and from an outside observer's perspective, it would appear to freeze as it approaches the event horizon. Now, in terms of time travel, the curvature of space-time around a black hole could theoretically allow for travel into the past. The warping of space-time near black holes might create paths or shortcuts in space-time, known as wormholes, that could potentially allow for time travel. However, these ideas are speculative and require further understanding of the nature of black holes and the limits of general relativity. Wormholes, bridges through space-time. One of the most intriguing ideas related to time travel is the concept of wormholes, which are theoretical passages through space-time that could create shortcuts between distant points in the universe. Wormholes are sometimes referred to as Einstein-Rosen bridges, after the physicists Albert Einstein and Nathan Rosen, who first proposed their existence in the 1930s. In essence, a wormhole is a tunnel with two ends, each located at separate points in space-time. If such a tunnel existed, it could, in theory, allow an object to travel from one point to the other faster than light could travel through normal space. This would create the possibility of instantaneous travel between distant regions of the universe. Wormholes are often depicted in science fiction as a means of time travel. If we could travel through a wormhole, the object or person entering the tunnel might travel from one point in time to another. This is because in some interpretations of general relativity, wormholes could potentially connect not just different places in space, but different points in time as well. Theoretically, if you could enter a wormhole that loops back on itself, you might be able to travel back in time. However, the idea of traveling through a wormhole raises significant challenges. First, the wormhole would need to be stable enough to allow an object to pass through it without being destroyed by the intense gravitational forces involved. Second, even if a wormhole could be created, it would require the presence of exotic negative energy to keep it open. Negative energy is a theoretical concept that, according to some models of quantum physics, could counteract the gravitational forces that would otherwise cause a wormhole to collapse. Unfortunately, negative energy has never been observed, and it remains an entirely theoretical concept. Despite the challenges, some physicists believe that wormholes could, in principle, be created in the distant future. The idea of traversing space-time through a wormhole remains a fascinating, though speculative, possibility for time travel. Closed time-like curves, a path to the past. Another theoretical concept that has gained attention in discussions of time travel is the idea of closed time-like curves, CTCs. A closed time-like curve is a path in space-time that loops back on itself, allowing an object to return to the same point in time from which it started. These loops in time are mathematically allowed in the framework of general relativity, particularly in the presence of certain cosmic structures, such as rotating black holes, known as Kerr black holes. The concept of a closed time-like curve suggests that time might not be a simple one-way progression. Instead, it could be possible to loop back through time, potentially allowing for travel into the past. In a sense, this would enable an object to experience time in a circular rather than linear fashion. For example, imagine traveling into the past and interacting with events that had already happened, possibly even influencing the course of history. This raises the possibility of paradoxes, such as the famous grandfather paradox, in which a time traveler goes back in time and inadvertently prevents their own existence by changing events in the past. The possibility of closed time-like curves suggests that, while time travel to the past may be mathematically possible, it could involve logical paradoxes that challenge our understanding of causality. Some physicists believe that the existence of such paradoxes could be a major obstacle to the possibility of time travel to the past. Others, however, propose that quantum mechanics might provide a solution, allowing for time travel that avoids such paradoxes. Time travel and the multiverse theory. An intriguing aspect of time travel is its potential connection to the multiverse theory. According to some interpretations of quantum mechanics, there could be an infinite number of parallel universes, each with its own timeline and set of physical laws. In the context of time travel, the multiverse could provide a way to circumvent the paradoxes that arise when changing the past. If time travel to the past were possible, it might not alter the timeline of our universe at all. Instead, it could create a new, separate timeline, an alternate universe in the multiverse. This idea, often referred to as the many worlds interpretation of quantum mechanics, suggests that when a time traveler makes a change in the past, they do not alter their original timeline, but instead create a new one. This would resolve paradoxes, as changes in the past would simply result in the creation of a new, parallel universe, rather than interfering with the traveler's original timeline. The multiverse theory presents a fascinating solution to the problem of time travel. If every possible outcome of a quantum event results in a new universe, then traveling through time might not have the catastrophic effects we fear. Instead, it could simply add to the infinite web of possible realities in the multiverse, offering a new way for time travel to exist without violating the laws of causality. Can we travel through time? Despite the exciting theoretical possibilities, time travel remains speculative at best. While Einstein's relativity and the idea of wormholes provide intriguing avenues for exploration, we currently lack the technology, energy, and understanding of quantum mechanics necessary to achieve time travel. The creation of stable wormholes, the harnessing of negative energy, or the construction of time machines that can manipulate space-time remain well beyond our capabilities. However, the fact that time travel is not currently possible does not mean it is impossible. As our understanding of the universe deepens, new breakthroughs in physics could open the door to time travel in ways we cannot yet imagine. For now, time travel exists primarily as a fascinating concept in science fiction and theoretical physics, but who knows what the future may hold? If humanity continues to push the boundaries of science, the dream of traveling through time could one day become a reality. One of the most fascinating and mind-bending concepts in the realm of time travel is the idea of wormholes. These theoretical passages through space-time could, in theory, serve as shortcuts between distant parts of the universe, or even between different points in time. While wormholes are often depicted in science fiction as portals that allow characters to travel to the past or future, the scientific reality of wormholes is both complex and speculative. Could wormholes actually allow for time travel? In this chapter, we will explore the nature of wormholes, how they might function, and the scientific theories that suggest they could one day be used for time travel. What is a wormhole? A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical structure in space-time that would connect two separate points in the universe. The concept of a wormhole was first proposed by physicists Albert Einstein and Nathan Rosen in 1935 as part of their work on general relativity. They suggested that the curvature of space-time could, under certain conditions, create a tunnel-like structure that connects two distant regions of space. Think of a wormhole like a tunnel with two ends, each located at different points in space-time. If you were to travel through this tunnel, you could theoretically reach your destination faster than you could by traveling through normal space. Essentially, a wormhole would allow you to take a shortcut through space-time, bypassing the distance between the two ends of the tunnel. While this idea sounds straightforward, the reality is far more complex. In the simplest depiction of a wormhole, imagine folding a piece of paper in half with 2 points on opposite sides of the fold. If you were to punch a hole through the paper, you would create a shortcut between those 2 points. Similarly, a wormhole would create a direct link between two distant points in space-time, bypassing the intervening space. While this is an interesting analogy, the actual mathematics of wormholes involves the curvature of space-time itself. The fabric of space-time is not a flat static backdrop, but a dynamic, flexible entity that can be warped and bent by the presence of mass and energy. According to general relativity, if a sufficiently massive object were to warp space-time enough, it could create a tunnel-like structure that connects two different points in space-time. Essentially, a wormhole. Types of wormholes. Wormholes, in theory, could take several different forms. The simplest and most well-known type is the traversable wormhole, which is a type of wormhole that could, in principle, allow for safe travel between two distant points in space-time. A traversable wormhole would allow an object or person to enter one end of the wormhole and emerge from the other, bypassing the intervening space. In theory, this could allow for faster-than-light travel, as the distance between the two ends of the wormhole would be significantly shorter than the distance that would be traveled through normal space. However, traversable wormholes come with their own set of challenges. One of the most significant problems is that wormholes are believed to be incredibly unstable. Without some sort of external support, the wormhole would collapse before anything could travel through it. This is because the intense gravitational forces at the ends of a wormhole would cause it to pinch off and collapse, preventing anything from passing through. To stabilize a wormhole, scientists have theorized that exotic matter with negative energy would be required to hold the tunnel open. Exotic matter is a theoretical form of matter that has properties opposite to those of normal matter, including negative energy density. Unlike regular matter, which has positive energy density and causes space-time to curve in a certain way, exotic matter would cause space-time to curve in the opposite direction, allowing it to hold the wormhole open. While exotic matter has not been observed, the mathematics of wormholes suggests that it would be necessary to stabilize the structure and allow for safe travel through a wormhole. Another type of wormhole is a non-traversable wormhole, which would not allow for any passage through it. These wormholes could exist, but they would be unstable or would collapse too quickly for anything to enter or exit. These types of wormholes may occur naturally in the fabric of space-time, but their practical use for time travel is unlikely. Despite these challenges, the idea of traversable wormholes remains a topic of serious research. If exotic matter or other unknown forms of energy were discovered, they could potentially be used to stabilize a wormhole, making time travel and faster-than-light travel possible. Wormholes and time travel. So how do wormholes connect to time travel? To understand this connection, we must consider how space-time itself behaves according to the theory of relativity. Space and time are not separate entities, but are part of a unified whole, the space-time continuum. This means that any curvature or manipulation of space also affects time, and vice versa. If a wormhole can bend space-time, then it could, in theory, also bend time. In a simple model of a wormhole, imagine two openings, one located in the present and the other in the distant past or future. By traveling through the wormhole, the observer could theoretically move from one point in time to another, bypassing the passage of time in between. This would allow someone to travel back in time or into the future without experiencing the intervening moments. In effect, the wormhole would act as a shortcut through time. For example, imagine that you enter a wormhole at one point in time and emerge at a different point in time. If you were to enter the wormhole at the present moment, the exit might be in the past or the future, depending on the specific configuration of the wormhole. In this scenario, you could theoretically travel backward in time to witness historical events or even change the course of history, at least in theory. However, this idea raises several profound questions, particularly regarding the grandfather paradox and the potential for causal loops. The grandfather paradox is a famous thought experiment in which a time traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth. If this paradox occurs, it would create a logical contradiction. If the time traveler was never born, how could they have traveled back in time to change the past? There are various potential solutions to these paradoxes, including the idea of parallel universes or many worlds interpretation. According to this view, changing the past would not alter the time traveler's original universe, but instead create a new timeline or reality. This would mean that any actions taken in the past would not have consequences for the traveler's original timeline, but would instead branch off into a new, separate reality. Wormholes and the multiverse. The idea of wormholes as time travel portals is often associated with the concept of the multiverse, the idea that our universe is just one of many, possibly infinite, parallel universes. In the multiverse model, each possible outcome of every quantum event creates a new universe, resulting in an ever-expanding collection of parallel realities. In this framework, wormholes could potentially connect different universes as well as different points in time within a single universe. The connection between wormholes and the multiverse theory is speculative, but it offers a potential solution to some of the paradoxes associated with time travel. If traveling through a wormhole to the past creates a new universe or timeline, then the time traveler could visit an alternate version of history without causing a paradox in their own timeline. In this sense, time travel through wormholes could be seen not as altering the past, but as exploring different parallel timelines or realities. Challenges to using wormholes for time travel. While the concept of using wormholes for time travel is captivating, there are significant challenges and unanswered questions that must be addressed before wormholes could become a viable method for traveling through time. One of the primary obstacles is the need for exotic matter with negative energy to keep a wormhole open. Without this exotic matter, a wormhole would collapse under the intense gravitational forces at its ends, preventing anything from passing through. Another major challenge is the size and stability of a wormhole. Wormholes that are large enough to allow for time travel would need to be incredibly stable to prevent them from collapsing or destroying anything that enters them. Theoretical models suggest that even if a wormhole could be created, it might be so small that only subatomic particles could pass through it. To make wormholes large enough to allow for the travel of human beings, we would need to understand much more about the fundamental nature of space-time and how to manipulate it on a massive scale. Finally, the question of whether wormholes even exist in the universe remains unanswered. While wormholes are theoretically possible according to general relativity, no observational evidence has been found to suggest that they exist naturally in the cosmos. Some physicists have proposed that black holes could act as natural wormholes, but this remains purely speculative, and we have no direct evidence to support the idea. Conclusion: are wormholes a path to time travel? While the concept of wormholes provides an intriguing theoretical pathway for time travel, there are still many unknowns and challenges to overcome before they could be used for practical purposes. The need for exotic matter, the instability of wormholes, and the lack of observational evidence all present significant obstacles. However, the idea of wormholes remains one of the most fascinating aspects of theoretical physics, and their potential connection to time travel continues to inspire physicists and science fiction enthusiasts alike. The idea that time travel could be possible through a wormhole challenges our traditional understanding of time and space. It forces us to think about the universe in new and unconventional ways, considering not just how space can be manipulated, but how time itself can be bent and altered. Whether or not wormholes will ever be used for time travel remains to be seen, but the exploration of this concept pushes the boundaries of human knowledge and imagination, opening up exciting possibilities for the future. As we delve deeper into the concept of time travel, we inevitably encounter one of its most perplexing and fascinating aspects: paradoxes. Time travel, particularly the idea of traveling backward in time, seems to open up a realm of possibilities that challenge the very nature of causality, logic, and the fabric of reality itself. If time travel to the past were possible, could we change the events that have already happened? Could we alter the course of history, prevent terrible events, or even meet our past selves? Or, as some physicists and philosophers argue, would the very nature of time prevent us from making any changes to the past at all? This chapter will explore the nature of time travel paradoxes, the most famous of which is the grandfather paradox, and examine the potential solutions that have been proposed. We will also look at how the multiverse theory, quantum mechanics, and other ideas in modern physics might offer ways to resolve the paradoxes inherent in time travel. While time travel remains purely theoretical, understanding the paradoxes it creates can offer profound insights into the nature of time, causality, and the universe itself. The grandfather paradox, the classic time travel conundrum. The grandfather paradox is perhaps the most well-known and classic example of a time travel paradox. It is a thought experiment that highlights the logical contradictions that arise when we consider traveling backward in time and changing events that have already occurred. The basic scenario goes like this. Imagine you travel back in time to a moment before your grandfather had children. While in the past, you accidentally prevent your grandfather from meeting your grandmother, or perhaps even cause his early death. The result is that your parents are never born, and therefore, neither are you. But if you were never born, how could you have traveled back in time in the first place to change the past? This creates a logical paradox. Your existence is a prerequisite for your time travel, but your actions in the past negate that existence. The grandfather paradox raises profound questions about causality and the nature of time. If we can change the past, then events seem to become mutable, which undermines the idea of a consistent timeline. It suggests that traveling backward in time could create contradictions, leading to the possibility that events could not have unfolded in the way they did, causing a paradox that fundamentally challenges the idea of linear time. Other paradoxes. Can the past be changed? The grandfather paradox is just one of many potential paradoxes that arise from the idea of changing the past. Time travel to the past raises questions about causality, the principle that every effect has a cause. In the context of time travel, the problem is that if events can be altered, we might no longer have a clear cause-effect relationship. Here are a few other common paradoxes that emerge from the idea of time travel. 1. The bootstrap paradox. This paradox involves a scenario where an object or piece of information is sent back in time, but its origin becomes unclear. For example, imagine you travel back in time and give Shakespeare a copy of Hamlet. Shakespeare then publishes the play, which you later read in your own time and bring back to Shakespeare. The question arises, where did the play come from? In this case, the play seems to have no original creator, creating a causal loop that cannot be resolved. The object or information exists, but no one is its original author or source. 2. The predestination paradox. This paradox occurs when time travelers find themselves caught in a loop of events that are predestined to happen. For example, imagine that a time traveler goes back in time to prevent a major historical event, such as a war or a disaster. However, upon arriving in the past, the time traveler accidentally causes the event to happen, fulfilling the very purpose they had set out to prevent. This paradox suggests that time travel might be inherently constrained by a kind of inevitability. No matter what actions you take, history will unfold in the way it is meant to. 3. The consistency paradox. This paradox revolves around the idea that events in the past must remain consistent with the present. For instance, if a time traveler goes back in time and changes something minor, they might inadvertently prevent the very circumstances that led them to travel back in time in the first place. The consistency paradox suggests that no matter what changes are made, the past must be consistent with the present, and thus, any attempt to change the past will either fail or be self-correcting. Can paradoxes be avoided? As we've seen, time travel introduces a host of paradoxes, most of which arise from the idea of changing the past. However, this doesn't necessarily mean that time travel to the past is impossible. Some physicists and philosophers have proposed ways in which these paradoxes might be avoided or resolved, offering potential solutions to the logical contradictions that arise from time travel. 1. The Novikov self-consistency principle. One of the most famous solutions to time travel paradoxes is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. According to this principle, the laws of physics would prevent any action that would create a paradox. In other words, the universe itself would correct any attempt to alter the past in such a way that it would lead to inconsistency. For example, if a time traveler were to attempt to kill their grandfather before he had children, some mechanism would prevent this from happening. Perhaps the time traveler would accidentally fail in their mission or be stopped by some external force. This principle suggests that the universe has a built-in consistency that prevents paradoxes from occurring. 2. The multiverse theory. Another potential solution to the paradox problem comes from the multiverse theory, which suggests that there are an infinite number of parallel universes, each with its own timeline. According to this theory, any action taken in the past that changes the course of events would not affect the original timeline, but would instead create a new, branching timeline. In this model, time travel does not lead to contradictions, because any change made in the past results in the creation of a new universe, which exists separately from the original one. This idea is often referred to as the many worlds interpretation of quantum mechanics, and offers a way to avoid paradoxes by suggesting that the timeline splits whenever a change is made. 3. Quantum mechanics and the many worlds. Interpretation. The many worlds interpretation of quantum mechanics is one of the most intriguing possible resolutions to time travel paradoxes. According to the many worlds interpretation, every quantum event that has multiple possible outcomes creates a separate branch of reality. In the context of time travel, this means that if a time traveler were to go back in time and change the past, they would not be altering their own timeline, but rather creating a new, parallel timeline. This concept would effectively resolve paradoxes because the traveler's actions would not affect their original universe, but rather create a new one in which the changes occurred. 4. Block universe. Theory. Another solution to time travel paradoxes is the block universe theory. This theory, also known as eternalism, suggests that all moments in time, past, present, and future, exist simultaneously in a block of space-time. According to this theory, time is not a flowing river, but a static structure in which all events are equally real. In a block universe, the past, present, and future are already determined, meaning that time travelers cannot change the past as it already exists within the structure of space-time. In this view, paradoxes are avoided because the future is just as fixed as the past, and any actions taken by time travelers were always part of the timeline. Quantum mechanics and causality. One of the central challenges in resolving time travel paradoxes is understanding the relationship between causality and quantum mechanics. At the quantum level, particles do not behave in a predictable, deterministic way. Instead, they exist in a state of superposition, meaning they can be in multiple states at once. Only when they are observed or measured do they collapse into a single state. Some physicists believe that this quantum uncertainty could offer a solution to the problem of time travel paradoxes. If time is inherently probabilistic rather than deterministic, it may not be subject to the strict cause and effect relationships we experience at the macroscopic scale. In this view, time travel might not create the logical contradictions that we expect, because the quantum nature of reality allows for multiple non-contradictory outcomes. Essentially, the universe may be able to adapt to time travel by incorporating multiple possibilities without causing a paradox. Time travel, a theoretical dilemma. Despite the fascinating theoretical solutions to time travel paradoxes, it is important to remember that time travel remains a highly speculative concept. While we can entertain the idea through the lens of physics and mathematics, there is currently no empirical evidence to suggest that time travel to the past is possible. Time travel to the future through time dilation is theoretically possible under the laws of relativity, but time travel to the past presents profound challenges that have yet to be resolved. Nevertheless, the discussion of time travel paradoxes provides valuable insight into the nature of time, causality, and the universe itself. Whether through the Novikov self-consistency principle, the multiverse theory, or the block universe theory, physicists and philosophers are continuously grappling with these paradoxes and exploring the fundamental structure of reality. And even though we may never achieve time travel in the way we see it in science fiction, These theoretical explorations continue to inspire our understanding of time, space, and the very fabric of the universe. The possibility of time travel into the future is one of the most intriguing aspects of the broader discussion about time travel. Unlike the paradoxes that arise when we consider time travel to the past, the journey forward in time is not only possible but also something we experience every day. But could we, in some way, accelerate the process and travel to the future at a much faster rate than the normal progression of time? Could we one day travel far into the future, to a time when humanity has evolved or perhaps even reached its ultimate end? In this chapter, we will explore the concept of time travel to the future, focusing on the scientific principles that allow for it, particularly through the lens of special relativity and general relativity. We will also delve into the implications of time dilation, how astronauts have already experienced time travel, in a sense, and the possibility of extreme future travel to distant futures, unimaginable societies, and a universe that has changed beyond recognition. Time travel to the future, the role of time. Dilation. At first glance, the idea of traveling to the future may seem purely theoretical or impossible, but time travel to the future is already a well-established concept in special relativity, one of the pillars of modern physics. According to Einstein's theory of special relativity, time is not a constant and unchanging flow. It is relative, meaning that time can pass at different rates depending on an observer's speed and position in space-time. The phenomenon known as time dilation is at the heart of this concept. Time dilation occurs when an object moves at a significant fraction of the speed of light. As an object approaches the speed of light, time for the object slows down relative to an observer at rest. This means that a person traveling at near light speeds would experience time passing much more slowly than someone who remains stationary. For example, imagine two identical twins. One twin stays on Earth while the other travels on a spaceship at near light speeds for a year. When the traveling twin returns to Earth, they will have aged only 1 year, but the twin who remained on Earth will have aged much more, perhaps decades. This is time dilation in action. The faster you travel, the slower time moves for you compared to someone at rest. By traveling close to the speed of light, you would effectively skip forward in time. The theoretical concept of time dilation has been confirmed through numerous experiments. One of the simplest and most compelling examples comes from the use of atomic clocks. In an experiment conducted in the 1970s, 2 atomic clocks were synchronized, and one was placed on a jet that flew around the world, while the other remained stationary on the ground. When the jet returned, the clock on the plane had ticked more slowly than the clock on the ground, confirming the effects of time dilation. While these effects are minuscule at the speeds we are currently capable of, they become significant when we approach relativistic speeds. Relativity and time travel. Into the future. Time dilation provides a mechanism for traveling forward in time, though the travel is not instantaneous or arbitrary. To experience time travel to the future in a meaningful way, you would have to travel at extremely high speeds, close to the speed of light. This is the principle behind time travel as understood in the context of special relativity. Let's consider the scenario of an astronaut traveling to the distant future. If an astronaut were able to travel at 99% of the speed of light, time would pass much more slowly for them than it would for people on Earth. The astronaut might travel for what feels like only a few years, but when they return to Earth, centuries could have passed. The time traveler would effectively have jumped into the future, bypassing the ordinary flow of time experienced by those who remained on Earth. This kind of time travel is possible, but it's important to note that it requires speeds that are currently unattainable. We have yet to build spacecraft capable of achieving even a fraction of the speed of light, and the energy required to accelerate an object to such velocities is beyond our current technological capabilities. However, the basic principles of time dilation have been demonstrated, and it's clear that in the future, if technology allows us to approach light-speed travel, time travel to the future will be possible. Gravitational time dilation. Time near a black hole. Another fascinating aspect of time travel to the future comes from general relativity, which expands upon special relativity by incorporating the effects of gravity on time. According to general relativity, massive objects, like stars, planets, and black holes, warp the fabric of space-time. The more massive an object is, the greater its gravitational pull, and the more it bends space-time. This warping of space-time has a profound effect on the passage of time. The closer an object is to a massive body, the more space-time is curved, and the slower time passes relative to an observer far away from the source of gravity. This phenomenon is called gravitational time dilation. One of the most extreme examples of gravitational time dilation occurs near a black hole, an object so massive and dense that not even light can escape its gravitational pull. As you approach the event horizon of a black hole, time slows down dramatically. To an outside observer, someone falling into a black hole would appear to freeze in time as they approach the event horizon. However, from the perspective of the person falling in, time would pass normally for them. If we could find a way to survive near a black hole, which, due to the immense forces involved, is unlikely with current technology, we could experience an extreme form of time travel. The passage of time near the black hole would slow down significantly, allowing the person to travel forward in time relative to those far from the black hole. While this scenario remains theoretical, it's based on sound physics and offers an intriguing possibility for time travel to the future, even if the conditions are harsh and survival is improbable. The possibility of time. Travel to the distant future. While time travel to the future through time dilation is theoretically possible, the implications of traveling far into the future are equally fascinating. If we could travel forward in time at relativistic speeds, we would witness a future that is radically different from the present we know. Over the course of millennia, stars will burn out, galaxies will drift farther apart, and the universe will continue to expand. The long-term future of the universe, as described by cosmologists, involves the slow cooling of the cosmos in a state known as the heat death or big freeze, a future in which all stars burn out, galaxies become isolated, and the universe becomes a cold, dark void. If time travel to the future were possible, we could witness the distant future of our universe. We might see the evolution of life forms, the rise and fall of civilizations, and the eventual decay of everything. The far future may be so distant that the concepts of matter, energy, and life as we know them would no longer exist. The heat death of the universe would mark a time when all thermodynamic processes cease and time itself becomes meaningless in a universe that has reached its final state. In addition to observing the future of the universe, time travel to the future could offer insight into the ultimate fate of humanity. If we could travel far enough into the future, we might witness the eventual extinction of human life, the rise of new species, or the unimaginable advancements of technology. Humanity's place in the cosmos may ultimately be fleeting, but time travel could allow us to glimpse the future and understand our role in the grand timeline of the universe. The challenges of time travel to the future. While time travel to the future is theoretically possible through time dilation, there are significant practical challenges. First, the velocities required to experience significant time dilation are currently far beyond our technological capabilities. Achieving near-light speeds would require an enormous amount of energy, and building spacecraft capable of such speeds would be an immense engineering challenge. Moreover, as we approach light speed, relativistic effects become more pronounced, making it increasingly difficult to accelerate further without infinite energy. Second, there are the physical challenges associated with traveling at such high speeds. The energy required to accelerate an object to near-light speeds is staggering, and the effects of high-speed travel on the human body are largely unknown. At relativistic speeds, particles in space would pose significant risks, as even a single collision with a small particle could release vast amounts of energy. Finally, there are the unknowns associated with traveling near massive objects, such as black holes. While gravitational time dilation near black holes could theoretically allow for time travel to the future, the risks involved in traveling near such extreme gravitational environments are immense. Black holes have such intense gravitational fields that they could easily tear apart any object that ventures too close. Even if we could find a way to safely approach a black hole, the effects of time dilation would still be limited to relatively small amounts of time compared to the vast stretches of time that we might hope to experience. Conclusion: time travel to the future, a real possibility. In summary, while time travel to the future is not only theoretically possible but has been demonstrated experimentally through the effects of time dilation, the practical challenges of achieving significant time travel remain immense. The idea of traveling forward in time by moving at relativistic speeds or near massive objects is grounded in established physics, and future technological advancements could one day make time travel to the future a reality. However, the journey into the far future presents its own set of challenges. Whether we travel to witness the heat death of the universe, the rise and fall of human civilizations, or the distant future of other life forms, time travel to the future offers a window into a world vastly different from the one we know today. But for now, time travel remains a theoretical concept, awaiting the breakthroughs in physics and technology that might one day turn it into a reality. As we continue to push the boundaries of our understanding of space, time, and relativity, we inch closer to unlocking the mysteries of the universe's ultimate fate and the possibility of time travel to the distant future. While time travel to the future is a fascinating concept and is theoretically supported by the principles of relativity and time dilation, the notion of traveling to the past remains one of the most intriguing and paradoxical aspects of time travel. The ability to travel back in time, to revisit history or potentially alter the course of events, raises fundamental questions about the nature of time, causality, and the very fabric of reality itself. The possibility of traveling to the past has fascinated thinkers for centuries. From H.G. Wells's The Time Machine to the grandfather paradox, time travel to the past raises profound challenges in both philosophy and physics. In this chapter, we will explore the theoretical aspects of time travel to the past, the paradoxes it presents, and the potential solutions that have been proposed by physicists and philosophers. The paradoxes of time. Travel to the past. One of the primary obstacles to time travel to the past is the paradoxes that arise from the idea of altering events that have already occurred. The most famous and widely discussed paradox is the grandfather paradox, a thought experiment that raises the question: if you travel back in time and change an event that is crucial to your own existence, such as preventing the birth of your grandparents, could you cease to exist? If you don't exist, how could you have traveled back in time in the first place to change the past? This paradox illustrates the logical contradiction that arises when time travel to the past is considered. If we could change events that have already occurred, we risk creating an inconsistency in the timeline. In the case of the grandfather paradox, the very act of traveling back in time and altering the past creates a loop that cannot be resolved within the same timeline. The grandfather paradox is not the only paradox related to time travel to the past. There are several other types of paradoxes that challenge our understanding of causality. 1. The bootstrap paradox. This paradox involves objects or information that are sent back in time, but their origin becomes unclear. For example, imagine you go back in time and give Shakespeare a copy of Hamlet. Shakespeare publishes it and you later read it, bringing it back to give Shakespeare. The question arises, where did Hamlet come from? It seems to have no original creator, creating a loop with no clear beginning. The bootstrap paradox challenges our understanding of cause and effect, suggesting that objects or information might exist without a clear origin. 2. The predestination paradox. In this scenario, a time traveler goes back in time to prevent a major event such as a war or disaster. However, the time traveler inadvertently causes the event to happen while trying to stop it. The paradox here is that the time traveler's actions are predestined to lead to the event they are trying to prevent. This paradox suggests that time, in a way, might be unchangeable. No matter what actions we take, the events of the past will unfold as they always have. These paradoxes are not just theoretical problems, they point to deeper issues with our understanding of time itself. If time travel to the past were possible, it seems that the very structure of reality could be undermined, leading to contradictions and loops that challenge the idea of a consistent, linear flow of time. So, how can we reconcile these paradoxes with the laws of physics? Can time travel to the past be reconciled with physics? While the paradoxes of time travel seem insurmountable, there are some solutions proposed by physicists that might allow time travel to the past without violating the laws of physics or creating logical contradictions. These ideas, while speculative, offer ways in which time travel could be theoretically possible without causing paradoxes. Closed time-like curves, CTCs, and general relativity. One of the most promising solutions comes from the theory of general relativity, which describes the curvature of space-time caused by massive objects. According to general relativity, space-time is not a fixed backdrop but a dynamic entity that can be warped by the presence of mass and energy. The warping of space-time can, in some cases, create paths that allow for travel back in time. These paths are known as closed time-like curves, CTCs. A closed time-like curve is a path through space-time that loops back on itself. In this scenario, an object traveling along a CTC could return to the same point in space-time at an earlier time, effectively allowing for travel into the past. In this way, the laws of general relativity do not prohibit time travel to the past. They simply suggest that it may be possible under very specific conditions. CTCs are theoretically possible, but they require extreme conditions, such as the presence of a rotating black hole or a wormhole, to exist. Care black holes and time travel. One of the most fascinating possibilities for time travel to the past arises from rotating black holes, also known as Kerr black holes. In 1963, physicist Roy P. Kerr proposed that rotating black holes, unlike non-rotating black holes, could create CTCs, paths through space-time that loop back in time. The intense gravitational forces around a rotating black hole could, in theory, create a stable time loop that allows an object to travel back in time. While this concept is mathematically plausible, the physical feasibility of entering a Kerr black hole and surviving the journey is highly unlikely. The singularity at the center of a black hole is thought to be a point of infinite density, where space-time breaks down and the known laws of physics cease to function. Additionally, the powerful gravitational forces near the event horizon would stretch and crush anything that came too close. Nevertheless, the possibility of time travel through a rotating black hole remains one of the most exciting ideas in theoretical physics. Wormholes and time. Travel to the past. Another possible way to travel through time comes from the concept of wormholes, hypothetical tunnels through space-time that could connect two distant points in the universe. As we discussed in Chapter 3, wormholes are predicted by the equations of general relativity, and while they remain theoretical, their potential for time travel is intriguing. A wormhole could, in theory, allow for travel between 2 points in space-time. If one end of the wormhole is stationary and the other is moved near a massive object or high-speed motion, time would pass more slowly at the moving end of the wormhole due to the effects of gravitational time dilation. By traveling through the wormhole, you could potentially go back in time to the point where the two ends of the wormhole were connected. Essentially, you would be traveling to the past relative to the stationary end of the wormhole. However, like the concept of rotating black holes, the practical challenges of creating and stabilizing a wormhole are immense. Theoretical models suggest that to keep a wormhole open, it would require exotic matter with negative energy, which has never been observed. Without this exotic matter, the wormhole would collapse before anything could pass through it. The grandfather paradox and consistency. As we explore these possibilities, it's crucial to consider how the grandfather paradox and other time travel paradoxes might be resolved. One idea proposed by physicists is that self-consistency is built into the fabric of space-time. This idea suggests that the universe would somehow prevent paradoxical situations from occurring. For example, if you tried to prevent your grandfather from meeting your grandmother, some force or event would arise to ensure that the timeline remains consistent and you would still be born. In this view, the universe self-corrects to prevent logical contradictions. One of the most famous proponents of this idea was Igor Novikov, who formulated the Novikov self-consistency principle. According to Novikov, the laws of physics would prevent any action that could lead to a paradox. In other words, the universe would ensure that time travelers' actions do not disrupt the past in ways that would create contradictions. While this principle is still speculative, it provides a way for time travel to the past to occur without causing paradoxes. Another potential resolution to the paradox problem comes from the many worlds interpretation of quantum mechanics. According to this view, every possible action creates a new branch of reality, meaning that any changes made in the past would not affect the time traveler's original timeline, but would instead create a new parallel universe. This interpretation allows time travel to the past to avoid paradoxes by creating a separate timeline for each alteration made, rather than affecting the original timeline. Time travel to the past, a possible yet elusive dream. While the theoretical framework for time travel to the past exists within the laws of general relativity, the practical challenges of achieving it are immense. Even if we could harness the energy and technology necessary to manipulate space-time, to create wormholes or travel close to a rotating black hole, there are still fundamental questions that remain unanswered. The need for exotic matter, the instability of wormholes, and the ultimate limits of physics near singularities make time travel to the past highly speculative. Despite these challenges, the idea of traveling to the past continues to captivate our imaginations. The possibility of revisiting historical events, preventing tragedies, or even altering the course of history is a powerful and alluring concept. Whether time travel to the past will ever become a reality remains to be seen. But the exploration of this idea has already led to groundbreaking advancements in our understanding of time, space, and the universe. Theoretical physics continues to push the boundaries of our understanding, and as we continue to explore the nature of space-time, we may one day find that time travel to the past is not only possible, but achievable if we can overcome the paradoxes and practical limitations that currently stand in our way. Time travel has long been a subject of fascination, not just because of the possibility of revisiting the past or traveling to the future, but because it challenges the very nature of causality, the fundamental principle that events in the universe follow a cause and effect relationship. In our everyday experience, we believe that causes precede their effects. A ball is kicked before it moves, a person's actions lead to consequences, and the past shapes the present. However, time travel introduces the potential for events to happen in reverse order, creating scenarios where effects precede causes or where the very fabric of cause and effect is altered. If we could travel through time, could we change the past and alter the course of events? Would the universe allow such disruptions to causality, or would the laws of physics prevent us from breaking the natural flow of time? These are some of the most profound questions raised by the concept of time travel. In this chapter, we will explore how time travel might affect causality, how the laws of physics might regulate or restrict time travel, and the philosophical implications of altering the past. The principle of causality and its role in the universe. Causality, the idea that every event or phenomenon has a cause, is a cornerstone of classical physics and our everyday understanding of the universe. It tells us that the universe follows a logical, predictable sequence of events, that the future is determined by the present and the past. Causality allows us to make sense of the world around us and to anticipate how actions will unfold based on their causes. In classical mechanics, causality operates in a deterministic manner. Given the state of a system at one point in time, the future of that system can be predicted with absolute certainty. This idea, articulated by Isaac Newton, was foundational for the development of physics and the natural sciences. For example, knowing the positions and velocities of planets, We can predict their future orbits with great precision. Causality in classical physics is a one-way street. Causes always come before their effects. In this framework, the concept of time is also simple. It is a linear, unidirectional progression from past to present to future. The flow of time is one of the constant parameters of the universe, a backdrop against which causes and effects occur. However, time travel, especially time travel to the past, forces us to reconsider the very nature of causality and whether it can be violated or altered. The causal loop, time travel's greatest challenge. One of the most intriguing and perplexing consequences of time travel is the concept of the causal loop, a situation in which an event's effect becomes its own cause, creating a closed loop of causality. A classic example of this is the grandfather paradox, where a time traveler goes back in time and prevents their own grandfather from meeting their grandmother. If the time traveler's grandfather never marries, then the time traveler would never be born. But if the time traveler was never born, how could they have gone back in time to prevent the marriage in the first place? The grandfather paradox is just one example of a causal loop, but it highlights a fundamental challenge to our understanding of causality. If time travel is possible, could the very act of traveling through time create logical contradictions, where the cause of an event is also the effect of that event? And if so, how can the universe resolve these contradictions? A closed causal loop is one in which an event is both the cause and the effect of itself. These loops can lead to infinite regressions, where events continuously feed into each other without a clear origin. For example, imagine a time traveler who goes back in time and hands Shakespeare a copy of Hamlet. Shakespeare then writes the play, and it is brought back to the future by the same time traveler. The question then arises, who wrote Hamlet? The play seems to have no true author, creating a loop with no clear origin or cause. Some physicists argue that causal loops are impossible because they violate the fundamental laws of logic and causality. In classical physics, causality must be maintained. An effect cannot precede its cause, and no event can be both the cause and the effect of itself. Thus, if time travel to the past were possible, it would appear to create a logical contradiction that the universe would not be able to resolve. The Novikov self-consistency principle. Despite the apparent paradoxes created by time travel, some physicists have proposed that the laws of physics might prevent such contradictions from occurring. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s, suggests that the universe would not allow any action that would create a paradox. According to this principle, the universe is self-consistent. If time travel to the past is possible, then any actions taken by time travelers in the past must be consistent with the timeline. In other words, even if a time traveler goes back in time and attempts to change the past, the universe will adjust itself in such a way that no paradox can arise. For example, if a time traveler tried to prevent their own grandfather from marrying, the universe might intervene to ensure that this event still occurs, perhaps through some unforeseen event that forces the marriage to take place. In this view, the universe corrects itself to ensure that time remains consistent, no matter what actions the time traveler takes. The Novikov principle essentially asserts that causal consistency is built into the fabric of space-time, and paradoxical situations simply cannot arise. While the Novikov self-consistency principle resolves the problem of paradoxes, it raises its own questions. For instance, it implies that time travel to the past could only occur in a way that preserves the timeline as it is. No changes could be made to the past that would alter the future. This could be seen as a kind of determinism built into the structure of the universe, where the future is fixed and unchangeable, regardless of any actions taken in the past. The many worlds interpretation and time travel. Another intriguing solution to the paradox of time travel comes from the many worlds interpretation of quantum mechanics. According to this interpretation, every possible outcome of a quantum event creates a new parallel universe or branch of reality. In the context of time travel, this suggests that when a time traveler goes back in time and alters an event, they do not affect their original timeline, but instead create a new branch of reality where the changes take place. In this model, time travel to the past would not create paradoxes because it would not alter the traveler's original universe. Instead, the changes made by the time traveler would create an alternate timeline, a parallel universe where events unfold differently. The original timeline, in which the time traveler existed and made the decision to travel, would remain unchanged. This idea offers a resolution to the grandfather paradox. If a time traveler prevents their own grandfather from marrying, they simply create a new universe where they were never born. However, in their original universe, the timeline remains intact, and the traveler still exists. The many worlds interpretation allows for a kind of time travel that avoids the paradoxes typically associated with altering the past. However, it also introduces the idea of an infinite number of parallel universes, each with its own timeline. This raises questions about the nature of reality itself. If time travel can create infinite parallel timelines, does this mean that all possible outcomes are realized in some universe? And if time travelers can visit alternate timelines, what does this mean for the idea of a single objective history? The role of quantum mechanics in causality. Quantum mechanics plays a crucial role in our understanding of causality and time travel. Unlike classical physics, which treats time and causality as deterministic and linear, quantum mechanics reveals that events at the smallest scales are governed by probability rather than certainty. The uncertainty principle suggests that at the quantum level, the future is not predetermined. It is a range of possible outcomes that are influenced by the observer's measurements. In the context of time travel, quantum mechanics suggests that causality may be more flexible than we once thought. Events in the quantum world are not strictly ordered in a linear fashion. Instead, particles can exist in multiple states at once, and their behavior is probabilistic rather than deterministic. This opens up the possibility that the flow of time might not be as rigid as we experience it at macroscopic scales. If time itself can be probabilistic at the quantum level, then perhaps the notion of a fixed timeline is an illusion, and time travel to the past could be less constrained by the laws of classical causality. The concept of quantum entanglement, the phenomenon where particles become linked in such a way that their states are instantaneously correlated, no matter the distance between them, further complicates our understanding of causality. If particles can be instantaneously connected across vast distances, what does this mean for the flow of time? Could time travel be linked to quantum processes in which events at the quantum level influence each other in ways that defy classical notions of cause and effect? Conclusion: time travel and causality. Can we break the rules? The concept of time travel raises profound questions about the nature of causality and the structure of the universe. While time travel to the future is theoretically possible and supported by the principles of relativity, time travel to the past presents significant challenges, particularly in terms of paradoxes and the logical consistency of events. The grandfather paradox, the bootstrap paradox, and other time travel conundrums highlight the tension between our intuitive understanding of cause and effect and the strange counterintuitive nature of time. Physicists have proposed various solutions to these paradoxes, including the Novikov self-consistency principle, the many worlds interpretation, and the idea that time may be probabilistic at the quantum level. These ideas suggest that the universe may have mechanisms in place to preserve causal consistency, or that time travel could create new parallel timelines, avoiding paradoxes and contradictions. While time travel to the past remains speculative, the exploration of causality, quantum mechanics, and space-time continues to challenge our understanding of reality. As we push the boundaries of physics and deepen our understanding of the universe, the possibility of time travel and the ability to break or bend the rules of causality may one day become a reality. Until then, the mysteries of time travel will continue to fuel our imagination, offering us a glimpse into the complex and fascinating nature of time itself. The idea of time machines is one of the most iconic and enduring concepts in science fiction. From H.G. Wells' The Time Machine to the sleek futuristic DeLorean in Back to the Future, Time machines have captured the human imagination for over a century. But beyond their depiction in popular culture, the question remains, could we ever build a time machine that allows us to travel through time, whether into the future, the past, or even across alternate timelines? The theoretical foundations for time travel already exist within the laws of relativity and quantum mechanics, and concepts such as wormholes and closed time-like curves suggest that time travel could, in some form, be possible. But building a time machine that could manipulate time to the extent that we envision in science fiction remains a daunting challenge. In this chapter, we will explore the scientific and engineering possibilities for constructing a time machine, the technological barriers we must overcome, and the potential implications for humanity if such a machine could one day be built. What is a time machine? At its core, a time machine is any device or mechanism that allows a person to travel through time, either into the future or the past. The concept of a time machine is based on the idea that time is not a constant linear progression, but something that can be manipulated or traversed. In the most basic sense, a time machine would allow us to move through time in a controlled manner. In science fiction, time machines often involve complex machinery or futuristic devices that enable individuals to move backward or forward through time at will. But time travel, in reality, would require the ability to manipulate the fabric of space-time, the four-dimensional continuum that includes the three dimensions of space, length, width, and height, and the one dimension of time. To understand how a time machine might work, we must look at the principles of space-time manipulation and consider the technologies and concepts that could potentially allow us to move through time. This includes the ideas we've already explored, like wormholes, time dilation, and closed time-like curves, as well as the challenges that come with manipulating the universe at such a fundamental level. Wormholes as time machines. One of the most intriguing potential candidates for a time machine comes from the concept of wormholes. As discussed in earlier chapters, a wormhole is a hypothetical tunnel through space-time that could connect two distant points in the universe. If such a tunnel could be stabilized and kept open, it could serve as a shortcut between 2 points in space and, theoretically, between 2 points in time. Wormholes are predicted by the equations of general relativity and, in principle, could connect not just different regions of space, but different points in time. A traversable wormhole would allow someone to enter the wormhole at one end and emerge at the other, bypassing the space between them, and, depending on the configuration of the wormhole, potentially traveling through time. For example, imagine a wormhole where one end is near a massive object, like a black hole, that warps space-time drastically, causing time to pass more slowly for that end of the wormhole. The other end could be far from the black hole, where time passes at a normal rate. A traveler entering this wormhole could theoretically experience time passing at a different rate, depending on which end of the wormhole they're located in. By adjusting the position of the wormhole, it might be possible to travel into the future, or, potentially, the past. However, this idea relies heavily on the existence of exotic matter with negative energy, a form of matter that has not yet been observed but is theorized to have the opposite properties of regular matter. Exotic matter would be necessary to stabilize a wormhole and prevent it from collapsing. Without exotic matter, any wormhole that forms would likely collapse before anything could travel through it. So while wormholes offer a tantalizing possibility for time travel, they are still very much in the realm of theoretical physics. The challenge of negative energy. The concept of negative energy is one of the most critical challenges when it comes to the idea of building a time machine. In order to keep a wormhole open, we would need exotic matter that has negative energy density, a form of energy that behaves oppositely to regular matter. While regular matter has positive energy and causes space-time to curve in one direction, creating gravitational attraction, negative energy would curve space-time in the opposite direction, helping to prevent the wormhole from collapsing. Exotic matter with negative energy has never been observed in nature, but some quantum theories predict its existence. In particular, the concept of vacuum energy, the lowest possible energy that a quantum field can have, could potentially give rise to negative energy. Some physicists believe that if we could harness vacuum energy or other forms of negative energy, we might be able to create a stable wormhole, and by extension, a time machine. However, creating and harnessing negative energy presents enormous challenges. Theoretical models suggest that negative energy might only be possible under highly specific conditions, and there's currently no experimental evidence to support its existence. Until we can confirm the existence of negative energy and learn how to control it, building a wormhole that could act as a time machine remains far beyond our technological reach. Time travel via time dilation. In addition to wormholes, time dilation, the effect in which time slows down for an object moving at high speeds, offers another potential avenue for time. Travel to the future. According to special relativity, as an object approaches the speed of light, time for the object slows relative to an observer at rest. This means that if you could travel at relativistic speeds close to the speed of light, you could theoretically skip forward in time. Imagine an astronaut traveling at nearly the speed of light on a spaceship for several years. While they experience time normally, their time on Earth would seem to pass much faster. When the astronaut returns, they may have aged only a few years, while decades or even centuries might have passed on Earth. This is, in a sense, a form of time travel, traveling into the future relative to someone else without traveling backward in time. Theoretically, the faster you travel, the more time dilation occurs, allowing you to jump into the future without experiencing the passage of time in the same way as those who remain on Earth. While this form of time travel to the future is grounded in relativity, achieving the necessary speeds for significant time dilation presents serious challenges. Even the most advanced spacecraft we have today are nowhere near capable of reaching the speeds required for noticeable time travel. Traveling at relativistic speeds would require enormous amounts of energy, and the effects of traveling at such speeds on the human body are not well understood. Closed time-like curves, CTCs, and time machines. Another theoretical possibility for building a time machine comes from the idea of closed time-like curves, CTCs. As discussed in Chapter 6, a CTC is a path through space-time that loops back on itself, allowing for time travel to the past. In the case of a CTC, an object could travel along the curve and eventually return to the same point in space-time, but at an earlier time. This concept has been explored in relation to rotating black holes, Kerr black holes, and wormholes. These objects, under certain conditions, could create CTCs that allow for time travel to the past. In this scenario, a time machine would not need to be a conventional machine at all. It could be a naturally occurring phenomenon, such as a rotating black hole or a wormhole. By entering the CTC, an object or person could theoretically travel backward in time. However, this concept remains speculative, and there are significant theoretical challenges to making such time machines practical. The conditions required for the creation of CTCs, such as rotating black holes or exotic matter, are not easily achievable, and even if they exist, they would likely be extremely dangerous to approach. Additionally, any attempt to build a time machine from a CTC would face the same problems of stability, causality, and paradoxes that we've discussed in previous chapters. The engineering challenge of building a time machine. Even if the theoretical foundations of time travel to the future and the past are sound, the engineering challenges of building a time machine are formidable. To create a stable wormhole, for instance, would require not only the discovery of exotic matter, but the ability to control and manipulate space-time on an unimaginable scale. The energy requirements for such a feat would be astronomical, far beyond anything humanity is currently capable of. Similarly, the idea of traveling close to the speed of light requires advances in propulsion technology that are currently far from realization. Even achieving a fraction of the speed of light would require enormous energy resources, and the effects of high-speed travel on the human body, including radiation exposure, acceleration forces, and other potential dangers, are not well understood. In addition to the technological challenges, there are the dangers associated with time travel itself. Traveling into the past, as we have seen, could create paradoxes that would disrupt causality and the fabric of the universe. Even if time travel to the future is possible, we would still have to consider the long-term consequences of such journeys. What would the traveler encounter in the far future? How would humanity cope with the implications of interacting with distant futures? Could we ever build a time machine? Building a time machine remains a distant dream, one that is constrained by our current understanding of physics and our technological limitations. While theories such as wormholes, time dilation, and closed time-like curves offer tantalizing possibilities, there is no empirical evidence to suggest that we can create the necessary conditions for time travel. Until we can confirm the existence of exotic matter, develop advanced propulsion systems, and overcome the paradoxes and challenges associated with time travel, the creation of a time machine remains firmly within the realm of speculation. However, this should not deter us from continuing to explore the nature of space-time, the possibilities of wormholes, and the mysteries of the universe. As we continue to push the boundaries of physics, new breakthroughs may one day make time travel a reality. Until then, the concept of the time machine serves as a powerful reminder of humanity's boundless curiosity and the desire to explore the deepest mysteries of existence. As we explore the theoretical possibilities of time travel, we are faced not only with scientific and technological challenges, but also with profound ethical questions. If time travel were to become a reality, it would have the potential to radically change the course of human history, and with it, the very fabric of morality, responsibility, and personal choice. How would we, as individuals and societies, handle the immense power to influence time itself? Time travel presents unique ethical dilemmas that go far beyond the conventional questions of right and wrong. It challenges our understanding of free will, personal responsibility, and the consequences of our actions. In this chapter, we will explore the ethical implications of time travel, focusing on questions such as whether we should attempt to alter the past, the moral responsibility of time travelers, and how we might navigate the complexities of changing history. Should we alter the past? The most obvious ethical dilemma associated with time travel involves the question of whether we should attempt to alter the past. If we had the ability to go back in time, would it be morally acceptable to change historical events to prevent tragedies, wars, or catastrophes? For example, if time travel were possible, would it be right to go back and stop atrocities such as the Holocaust or slavery? Could the elimination of such historical wrongs create a better future, or would it come with unforeseen consequences? At first glance, the idea of using time travel to erase past atrocities may seem like a noble endeavor. After all, if we had the ability to stop suffering, pain, and injustice, wouldn't it be morally right to do so? However, the ethical ramifications of such actions are not so clear-cut. Changing the past could have unintended consequences, leading to what is known as the butterfly effect, the idea that even small changes in the past could have massive, unpredictable effects on the future. For instance, if a time traveler were to prevent a major historical event like the rise of a dictator, it might seem like a positive outcome. However, we cannot predict the full scope of the consequences. In trying to prevent one tragedy, the time traveler might inadvertently cause another, one that could be even worse. The future that emerges from such changes could be far from the ideal that was envisioned, and what seems like a good action could result in a future that is fraught with new challenges, injustices, or unforeseen consequences. Moreover, even if time travel could erase tragic events, it might also eliminate important lessons learned from those events. History, with all its flaws and imperfections, shapes the way societies evolve and adapt. If we were to erase a key historical event, we might risk robbing future generations of the opportunity to learn from the past and to ensure that the mistakes of history are not repeated. Thus, the ethical question of whether we should alter the past hinges on the potential for unintended consequences and the moral complexity of intervening in events that have shaped the world as we know it. In this sense, time travel to the past raises the difficult question: Is it morally permissible to change history, even for the better, if we cannot fully comprehend the consequences of those changes? The moral responsibility of time travelers. If time travel becomes a reality, the moral responsibility of the time traveler becomes a central concern. Those who have the power to alter time will hold immense responsibility, as their actions could have far-reaching effects on the lives of countless individuals. The question arises, what ethical principles should govern the actions of time travelers? How do we ensure that time travelers act in ways that promote good rather than harm, while recognizing the profound uncertainty that comes with changing time? Time travelers would need to operate with a high degree of caution, as their actions could ripple through history in ways that are impossible to predict. Even the most well-intentioned intervention could lead to negative consequences. The time traveler might believe they are making a positive change, but the long-term effects could be far from what was anticipated. In this sense, the ethical responsibility of time travelers is akin to that of anyone with great power. It requires careful consideration, foresight, and humility. The concept of do no harm could serve as a guiding principle for time travelers. If we had the ability to change the past, we would need to consider whether our intervention could cause more harm than good. The temptation to fix the past might be overwhelming, but the moral dilemma remains. How do we measure the potential harm caused by changes to the timeline? And how do we decide what counts as good or bad when it comes to shaping history? For instance, what if a time traveler went back in time to prevent the creation of an innovative invention that in the future would save millions of lives? Would they be morally justified in preventing that invention, even if it led to a better present? The notion that history is a chain of events, each affecting the next, makes the ethical calculus of time travel incredibly complex. The ethics of time travel to the future. While much of the ethical conversation around time travel centers on the past, traveling to the future also raises important ethical questions. If we could travel into the future, would we have the moral right to bring back knowledge or technology that could drastically alter our present? For example, imagine if a time traveler from the future were to bring back advanced medical knowledge that could cure diseases, extend life, or eradicate poverty. While these outcomes would seem undeniably positive, the ethical implications of such actions are not so clear-cut. Bringing knowledge from the future could give certain individuals or groups an unfair advantage over others, creating a power imbalance and potentially destabilizing societies. The sudden appearance of advanced technology or knowledge could have far-reaching consequences, such as economic upheaval, social inequality, or even the disruption of fundamental cultural norms. The time traveler would need to consider how the knowledge they bring back might impact the world, and whether it is morally acceptable to alter the course of history by introducing futuristic concepts. One particular ethical concern involves the idea of technological inequality. If future knowledge were brought back to the present and selectively distributed, it could lead to the emergence of a class of people who possess knowledge or technology far beyond the capabilities of the majority. This could exacerbate existing social divisions and create a future that is even more unequal than the one the time traveler originally sought to improve. Furthermore, time travelers could be faced with the dilemma of whether to intervene in the future they observe. If a time traveler were to see an impending catastrophe, such as an environmental disaster or a war, should they intervene to prevent it? If time travel is possible and future events are observable, the ethical question of whether to change the future becomes just as complex as changing the past. Does the traveler have the right to intervene in the future of humanity, or should they allow the course of history to unfold naturally? Personal ethics, the temptations of time travel. On a more personal level, time travel would present ethical challenges for the individual traveler. If someone had the ability to visit the past or future, could they use it for personal gain? For instance, could a time traveler go back to a point where they made a poor decision, erase the mistake, and make a better choice? Would it be morally acceptable for someone to use time travel to accumulate wealth, gain fame, or avoid personal hardships? The temptation to use time travel for personal gain could be immense. For example, A person could go back in time and place bets on stock market outcomes or use knowledge of future events to manipulate outcomes in their favor. Such actions could create a vast imbalance of power and undermine the fairness and integrity of social and economic systems. In this sense, time travel would not only require a careful consideration of the effects on the broader world, but also an evaluation of the individual traveler's personal ethics. The issue of moral agency would also come into play. If time travelers can alter events, then they also take on the responsibility for the consequences of those changes. Should time travelers be held accountable for their actions, even if they are from a different time period? Would the ability to travel through time make individuals more or less responsible for the outcomes of their decisions? The long-term ethical impact of time travel. The ethical implications of time travel extend beyond the individual actions of time travelers. Time travel could have long-term, unforeseen effects on humanity as a whole. The mere existence of a time machine could lead to a future where people try to alter their own timelines or escape from the consequences of their actions. It could create a future where people constantly seek to manipulate the past to achieve personal or political goals, undermining the very notion of a stable, shared reality. The existence of time travel could also raise difficult questions about identity and authenticity. If people can travel to different points in time, what happens to the individual's sense of self and their place in history? If a person can change their past, does it alter who they are, and can they still be held accountable for their actions? The very concept of personal responsibility could be called into question in a world where the past is mutable and the future is an open question. In the long run, time travel could present a serious ethical challenge for the stability and continuity of society. The temptation to rewrite history or shape the future could lead to a fragmentation of reality itself. If everyone had access to time travel, could a stable, cohesive society exist, or would time become a chaotic, ever-shifting force where the past and future are constantly rewritten? Conclusion: the ethics of time travel, a responsibility beyond measure. The ethical questions surrounding time travel are as complex and multifaceted as the concept of time itself. While the possibility of traveling through time offers great potential for positive change, such as preventing disasters, curing diseases, or advancing knowledge, it also comes with significant moral risks. Time travel to the past could lead to unintended consequences, paradoxes, and the erasure of valuable historical lessons, while time travel to the future raises concerns about technological inequality and the disruption of the natural course of history. The power to change the past or glimpse the future would place immense responsibility on those who wield it. Time travelers would need to act with caution, self-awareness, and humility, always considering the long-term impact of their actions. Just as we would not want to tamper with the natural order of the universe, we must carefully consider the ethical implications of altering time itself. In the end, time travel is not only a scientific or technological challenge, but a profound ethical dilemma, one that requires us to confront our deepest values, responsibilities, and understanding of reality. Time travel, a concept that has captured the human imagination for centuries, continues to be one of the most captivating ideas in both science fiction and theoretical physics. From the first fictional time machines crafted by H.G. Wells in The Time Machine to the modern portrayals in films like Back to the Future and Interstellar, the allure of traveling through time, whether to the past or future, has been a driving force in our exploration of what is possible. But despite its deep roots in popular culture, the question remains, will time travel ever become a reality? In this final chapter, we will explore the current state of time travel research, examining the cutting-edge scientific theories that provide a framework for the possibility of time travel. We will also assess the technological barriers that must be overcome, the philosophical and ethical challenges, and the potential impact of such a discovery on humanity and our understanding of the universe. With so many unknowns and uncertainties, is time travel something that could one day become reality, or is it destined to remain in the realm of fiction and theory? The current scientific understanding of time travel. At the forefront of time travel theory is Albert Einstein's theory of relativity, both special and general. These groundbreaking ideas fundamentally altered our understanding of space, time, and the universe. The theory of special relativity, published in 1905, introduced the concept that time is not a constant universal measure. It is relative and can be altered depending on an object's motion relative to an observer. The faster an object moves, the slower time moves for it. In essence, this was the first scientific breakthrough that suggested that time travel, or at least time dilation, might be possible. Further exploration of general relativity in 1915 expanded this understanding, showing that space and time are not separate entities, but part of a unified fabric called space-time. General relativity also proposed the idea that massive objects, such as stars, black holes, or even entire galaxies, could warp space-time, creating the conditions for phenomena like gravitational time dilation, where time passes more slowly near a massive object. This laid the groundwork for a kind of time travel to the future. However, while these theories allow for the possibility of time dilation, where a person traveling at relativistic speeds experiences time much more slowly than someone at rest, they do not directly provide a means of traveling backward in time, which is where the real challenge of time travel lies. Theoretical possibilities for time travel. As we've explored throughout this book, there are several theoretical concepts that could, in principle, allow for time travel. These ideas, while rooted in the fundamental principles of physics, remain speculative and untested. Let's review the most prominent concepts. 1. Wormholes. These are hypothetical tunnels through space-time that could, in theory, connect two distant points in both space and time. If a stable wormhole could be created, it might allow for instantaneous travel between these points. The potential for using wormholes for time travel exists, but stabilizing them, particularly with the required exotic matter to prevent their collapse, remains a major obstacle. No experimental evidence for the existence of wormholes has been found, though they remain a central topic of theoretical research. 2. Rotating black holes and closed time-like curves, CTCs. The idea that rotating black holes, also known as Kerr black holes, might permit time travel comes from the theoretical construct of closed time-like curves, CTCs. In essence, a CTC is a path through space-time that loops back on itself, creating a closed loop that could, in theory, allow a time traveler to return to a past point in time. While CTCs are permitted in the equations of general relativity, there are numerous challenges, including the extreme dangers posed by the gravitational forces near black holes, making this a more speculative pathway for time travel. 3. Time machines. Based on exotic matter, one potential solution to the issue of time travel is the use of exotic matter, hypothetical matter with negative energy density, to stabilize a wormhole or create a time machine. Exotic matter would be necessary to keep a wormhole open and prevent it from collapsing under the immense gravitational forces it would create. Despite the theoretical models suggesting that negative energy could make this possible, no exotic matter has been observed, and the ability to create or harness it remains one of the greatest unsolved mysteries of modern physics. 4. Cosmic strings and time loops. Another idea proposes that cosmic strings, hypothetical one-dimensional defects in spacetime, could provide the framework for creating time loops. These strings, which are believed to be remnants from the early universe, could, in theory, warp spacetime enough to allow for the creation of time loops. This is still highly speculative, but it adds to the growing list of possible theories for time travel. While each of these theories provides a potential framework for time travel, they also come with significant challenges and unanswered questions. The physics of time travel may not be fully understood yet, and the energy requirements to manipulate spacetime in such a way are far beyond anything we can currently achieve. Technological barriers to time travel. Despite the intriguing possibilities, there are substantial technological barriers to making time travel a reality. The fundamental problem is the energy requirements. In order to manipulate space-time in such extreme ways, as required for both forward and backward time travel, we would need to control enormous amounts of energy. For example, creating or stabilizing a wormhole would require energy on a scale far beyond anything humanity has ever produced. Even if exotic matter with negative energy could be found, manipulating it to the point where it could stabilize a wormhole would require technologies that are not only theoretical, but almost unimaginably advanced. The creation of stable, traversable wormholes, black hole manipulation, or the ability to reach relativistic speeds, all of which would be required for practical time travel, presents enormous engineering challenges. Furthermore, we would need to understand the consequences of manipulating space-time. Causal paradoxes such as the grandfather paradox could be a significant problem, and our current understanding of the universe suggests that any tampering with the past could have profound consequences on the present. Would time travel disrupt the timeline, or would the universe self-correct to maintain consistency? How could we ensure that time travel does not harm the fundamental structure of reality itself? The multiverse and time travel. Parallel timelines. An interesting concept that has emerged from discussions of time travel is the multiverse theory. According to this theory, there are an infinite number of parallel universes, each with its own timeline. In this model, if time travel were possible and someone were to alter the past, they would not change their own timeline, but would instead create a new parallel timeline or reality. This would prevent paradoxes such as the grandfather paradox, because the original timeline would remain intact and only a new timeline would be affected. The multiverse theory provides an elegant solution to the paradoxes of time travel by suggesting that changes in the past don't necessarily alter the original timeline, but create a new one. This could mean that time travelers, instead of altering their own history, are simply creating new versions of reality, parallel universes where different events play out. While the multiverse theory has been suggested by some interpretations of quantum mechanics, it is still highly speculative, and there's no direct evidence for the existence of parallel universes. However, the idea has captured the imagination of both physicists and science fiction writers alike, offering a potential escape from the paradoxes of time travel and opening the door to endless possibilities for exploration. Time travel and the future of humanity. If time travel were to become a reality, it could have profound implications for humanity and our understanding of the universe. The ability to travel forward in time would allow us to witness the future of our civilization, to see the long-term effects of our actions, to understand how humanity might evolve, and to glimpse the eventual fate of the Earth and the universe. This could give us invaluable insight into the challenges we will face in the coming centuries and millennia, potentially allowing us to make better decisions in the present. On the other hand, the ability to travel back in time could have a dramatic impact on our understanding of history and our relationship with the past. If we could visit important moments in history, we could gain a deeper understanding of the events that shape the world we live in today. But with this power comes great responsibility. As we have discussed, altering the past could have unforeseen consequences, and tampering with history might not only be dangerous, but could undermine the lessons that history has to offer. Moreover, the ability to travel through time raises questions about free will and determinism. If we can travel to different points in time, does this mean that time itself is fixed, with events already predestined? Or is time a fluid, dynamic entity shaped by our choices and actions? If time is malleable, how do we balance the power to change events with the ethical responsibility of preserving the timeline? Will time travel ever be possible? The potential for time travel is still very much a theoretical concept. The scientific theories that provide a framework for time travel, such as general relativity, wormholes, and the multiverse theory, are well established in physics, but they remain speculative when it comes to practical applications. Even though the laws of physics do not prohibit time travel, the technological, energy, and ethical challenges are immense. So, will time travel ever be possible? The truth is, we don't know. The future of time travel depends on the discoveries and breakthroughs that are yet to be made. As our understanding of space-time deepens and our technological capabilities evolve, we may one day unlock the secrets of time travel. But for now, it remains an exciting frontier in theoretical physics, one that continues to inspire scientists, philosophers, and science fiction enthusiasts alike. In the end, the quest for time travel is not just about the possibility of traveling through time, but about pushing the boundaries of human knowledge. Whether or not we ever build a functioning time machine, the pursuit of time travel forces us to rethink the nature of time itself, the structure of the universe, and our place within it. The future of time travel is uncertain, but the journey to understand it will continue to challenge our imagination and expand our understanding of the cosmos.